Hey everyone, welcome back. Today we're going to go through LeetCode 2910, minimum number of groups to create a valid assignment. This is one of those questions that had a 90% rejection rate, but for some reason was still rated as medium, which is kind of questionable and pretty discouraging to see. But anyway, let's briefly recap the problem description. So we're given an array nums, and we're also told that a valid assignment meets the following conditions. We need to group all the values in nums such that each group contains the same values, and for any two groups, the absolute value between the cardinality of the two groups has to be less than or equal to 1. We're also told that we need to return the minimum number of groups in such a valid assignment. So the first observation we can make is that we need to base our answer on the element that appears the least frequently. We want the minimum number of groups, and we also want the sizes of our groups to be within 1 unit apart. So therefore, we want the largest possible group size for the element that occurred the least frequently, and the group sizes we choose for all our other elements must be adjusted accordingly to the group sizes we choose for our least frequent element, meaning that they should be plus or minus 1 of our chosen group size. That was a really long sentence. If you didn't catch that, I recommend you rewind a couple seconds and listen to that again, because it's a key part of understanding the solution. So, how do we base our answer on the least frequent element? Well, imagine we had one group of size 10 and another of size 13. Then the solution here is to split the group of 10 into two groups of size 5, and to split the group of 13 into groups of 4, 4, and 5. How did we arrive at that answer? Well, one way is to find the largest prime factor of 10 and then see if we can use that in combination with 4 to split 13. So then we may start thinking about approaches involving prime factors and greatest common denominator algorithms, since there are lots of well-established algorithms out there for this kind of thing. For example, we could use a sieve to identify prime numbers, and we could use Euclid's algorithm for finding the greatest common divisor between two numbers. However, I chose not to do any of that. Now you may be wondering why. Well, a couple reasons. The first is that even though this is a pretty tough problem, it is labeled as medium. Medium questions typically don't require you to leverage lesser-known algorithms, and I would say this rabbit hole we're heading down about prime numbers is starting to veer off track of a medium. The second clue is kind of a LeetCode specific thing that happens a lot, and my instincts told me to check the constraints of the input parameters. We had an example of this in my previous video for LeetCode 2857, count pairs of points with distance k, where we could actually just check all possible partitions for a given set. And if you take a look at the constraints here, you'll see that we can do the same. The maximum length of the list is 10,000 elements, so that means that the largest size of any group of the same elements is going to be 10,000. That's great, because that means we can just test all possible partitions of the least frequently occurring element, and see if that partition size works for all the other groups. I'll also acknowledge here that I saw a lot of people saying they used binary search, or at least tried to. I deliberately chose not to here. I'm approaching competitive programming from a software engineering standpoint, meaning that I'll only choose a complex solution if it yields meaningful benefits over a simpler solution. Doing a linear scan over 10,000 elements versus doing a logarithmic scan over 10,000 elements is not really that different. If we were comparing a linear scan to a logarithmic scan over 1 billion elements, that would be a different story. So let's walk through a solution sketch followed by a specific example. We'll set a result of 0, and then we'll iterate from 1 to our minimum frequency, and these numbers will represent our current guess as to what partition size we should be using for most of our groups. Our helper function will then calculate how many groups we need to form using the current partition size plus 1. Finally, we'll return the result. Let's see how we determine the number of groups. We need to be a bit careful because we can use both the guessed partition sizes as well as the guessed partition size plus 1. First, let's see how many groups we have and how many elements we have left over if we strictly use the guessed partition size. If the remainder is larger than num groups, we return infinity to denote that this is not a valid partition. Now, you may be asking yourself, why? If you're not sure, pause the video, and I'll reveal the answer in 3, 2, 1. So this is actually much easier to see when you have an example in front of you. Let's pretend that the current frequency we're looking at is 33, and the current guessed partition size is 10. Then we have 3 groups of 10 and 3 as a remainder. If we have remainder equal to the number of groups, then we can redistribute each of these remaining elements into our existing groups. So we end up with 3 groups of 11, which is valid since all 3 groups have a difference of less than or equal to 1. Similarly, if we had 32 as our frequency, we could redistribute the remaining 2 elements to 2 of our groups of 10, and we'd end up with 2 groups of size 11 and 1 group of size 10. And again, this is valid because 11 and 10 only differ by 1. However, if we had a frequency of 34 and partition size of 10, then we'd have a remainder of 4. If we distributed these 4 elements evenly among the 3 groups of 10, we'd have 1 group of 12 and 2 groups of 11. Now, this is technically a valid configuration because 12 and 11 also only differ by 1. But remember, the definition for this helper function says we're only checking the number of groups we need, assuming that we can only use the provided partition size or partition size plus 1. Since our current guessed partition size is 10, 12 is out of scope for our current task, and is therefore an invalid group configuration in the context of this function. So we return infinity. Now for the final step of this function, we need to add the number of groups to our running total. Since we now have this condition that returns infinity, we know for a fact that all our elements can be partitioned into groups of partition size or partition size plus 1. We don't know how many of each we have though. Can you think of a simple expression in one line that captures this? Think about it and pause the video. I'll reveal the answer in 3, 2, 1. The answer is that we can just take the ceiling of true division between frequency and partition size plus 1. We need to consider 2 cases here to see why this works. The first is that partition size plus 1 evenly divides frequency, and the second is when it doesn't evenly divide frequency. If partition size plus 1 evenly divides frequency, then all of our groups must have size guessed partition size plus 1. That's like the example we had earlier where we had a total of 33 and a partition size of 10. 10 plus 1 is 11, and 11 evenly divides 33 into 3 groups. This is a valid case since all the groups have a difference cardinality of 0. So we can see that in this case, the ceiling function is a no-op, and we do indeed get the correct number of groups using this expression. If partition size plus 1 does not evenly divide frequency, then that means we have at least one group that still has partition size. In this case, that's the orange and turquoise groups. We can see that in this case, the ceiling of frequency divided by partition size plus 1 is going to be the ceiling of 31 divided by 11, which is equal to 3. So we can see that our ceiling function takes care of both cases, where partition size plus 1 does and does not evenly divide the current frequency. And then, finally, we just return the result in this helper function, and we can call it a day. And that's conceptually how we're going to solve this problem. Let's jump into the code. We'll first gather the counts of each unique element in our array, and we'll only keep the values in this dictionary because only the group sizes matter, not the elements within the group. We'll then iterate from 1 to the minimum frequency, and set result to the minimum of our current result and the number of groups we derive from trying the current guessed partition size. And now, let's fill in our helper function with the logic we described earlier. We iterate over all frequencies and check whether the remaining elements can be distributed evenly among the groups of size guessed partition size. If not, then we return infinity. Otherwise, we add the result of ceiling dividing frequency by partition size plus 1, and we return the result. And if we submit this answer, we can see that we beat 100% of all submissions for this question. If you found this solution helpful, please like, comment, and subscribe for more. I hope to be your definitive source of help for all tough programming problems. Thanks, and I'll see you in the next video.